Hello everybody. In this very short lessons, we will be talking about the fundamental physics of TG21. In order for us to get into the meat of this lesson, I just want to talk a little bit about the general objective of radiation therapy. Now, the success of radiation therapy depends strictly on the accuracy with which the prescribed dose is delivered to the target or the tumor. But the primary objective of radiation therapy really is to deliver a maximum dose to the target or the tumor, but at the same time spare the surrounding healthy tissues as well as the surrounding organs at risk. In order for us to ensure that we maximize the tumor control probability and minimize the normal tissue complication probabilities, we need to make sure that the dose delivered to the target is within 5% of the planned or prescribed dose. This essentially necessitates the need for improved accuracy in the dosimetry of high electron, photon or electron beams. This brings us to the crux of the matter, TG21. TG21 is actually one of the foundational dosimetry protocol designed to provide qualified medical physicists with an accurate method for determining the absorbed dose to water for a medical linear accelerator. It provides an essential framework for the determination of the essential parameters or factors in determining the absorbed dose to water. Now, one thing that I like about TG21, even though it is outdated because it has been replaced by TG51, is that it is very rich with some of the fundamental concepts required for the understanding of TG51. And therefore the objective of this lesson really is to look at the fundamental physics of TG51 because it to look at the fundamental physics of TG21 because it begets TG51. The very first concept that we will talk about will be particle fluence. In order to understand particle fluence, keep in mind that any X-ray beam emitted from a target, or let's say a gamma ray beam emitted from a radioactive source, consists of a large number of photons. And this photon or the spectrum usually have a variety of energies. In other words, the photons are normally not monoenergetic. Suppose that we have an imaginary sphere and the cross-sectional area of the sphere is dA. If we incident a certain number of particles on this sphere dN, then the particle fluence is simply defined by the quotient dN all divided by dA. Simply defined by the quotient dn all divided by dA. This means that the SI unit for fluence is simply per meters squared. Per meters squared. Now, N or dN represents the number of photons or particles incident or that enters the imaginary sphere with cross-sectional area A. There's another term that we call the fluence rate or flux density. The flux density psi is equal to simply the rate at which the particle fluence changes. The rate at which the particle fluence changes. If these particles are incident at right angles onto the cross-sectional area, then we will be dealing with planar fluence, which is simply equal to the number of particles incident on the surface divided by the cross-sectional area of the surface. Understand that whether the particles are incident obliquely or perpendicular to the plane containing the cross-sectional area, the number of particles hitting the spheres is the same. The next term that we will talk about will be energy fluence. Now, energy fluence really is a physical quantity that measures the total radiant energy impacted within a given sphere of cross-sectional area dA. Now, suppose that we have dN particles incident on a sphere with a cross-sectional area dA, with each particle carrying energy E. Then the total radiant energy dr will be equal to the energy carried by one particle divided by the total number of particles. The energy fluence phi is equal to dr all divided by dA. In other words, the energy fluence phi will be equal to E dN all divided by dA. But what do we know? We know that dN over dA is simply the particle fluence. This would mean that the energy fluence is just going to be equal to E multiplied by the particle fluence. Keep this in mind. This equation is very important. We are going to use this equation pretty soon. So the next term that we will talk about is kmA. kmA is an abbreviation that stands for the kinetic energy release per unit mass. Essentially, kmA measures the sum total of the initial kinetic energy of all the ionizing particles released in the medium per unit mass as a result of the interaction of that particular medium with the incident photons on it. What this means is that kmA is simply defined as the quotient between dEtr divided by dm, where EtR represents the sum of the initial kinetic energies of all the charged ionizing particles, whether electrons or positrons, liberated by photons in a given material of mass dm. Now, if you notice carefully, you realize that kmA has the unit of Gray, joules per kilograms. joules per kilograms. Now, for a given beam traveling through a medium, the kmr at any given point is proportional to the photon energy flowing at that given point. It makes sense, right? The initial kinetic energy of the charged particles liberated in the medium literally is proportional to the energy flowing of the incoming or incident radiation. So mathematically, the kmr is equal to the energy flowings multiplied by the average mass energy transfer coefficient. The mass energy transfer coefficient really is simply a coefficient that measures the amount of incident energy, that measures the amount of energy transferred to the liberated charged particles within a given medium. Now, what you need to keep in mind is that there is a relationship between the mass energy transfer coefficient for the medium and the average mass absorption coefficient. Now, the average mass absorption coefficient mu En is equal to the average mass energy transfer coefficient multiplied by 1 minus G bar. The constant G bar really represents the average fraction of the electron energy loss due to the radiative processes. What this means is that kmr K has two portions. You have the collision kmr plus the radiative kmr. The collision kmr plus the radiative kmr. Now, collision kmr is responsible for dose, while radiative kmr is not responsible for dose. Therefore, throughout our conversation beginning henceforth, we will be more focused on collision kmr. Now, keep in mind, let's call this equation 1. Let's call this equation 2. This is equation 3. And this is equation 4. So just to recap the main points, we know that kmr is proportional to the photon flowings multiplied by the average mass energy transfer coefficient, and this is equal to the collision kmr plus the radiative kmr. Now, the collision kmr is equal to the energy flowings multiplied by the average mass absorption coefficient of that particular medium multiplied by the average mass absorption coefficient of that medium, which implies that the radiative kmr is equal to simply the energy flowings multiplied by the average mass absorption coefficient of that medium multiplied by G bar divided by 1 minus G bar, where this constant essentially is a factor that gives us the fraction of the energy lost due to radiative processes. So when radiation or when a non-ionizing radiation such as photons interact with matters, it transfers its energy to secondary electrons, so it becomes KMR, and KMR is transferred to dose. Keep that in mind. KMR becomes dose. The next term that we will explore will be exposure, and we will look at the relationship between exposure and the dose. But first, we will look at the relationship between exposure and KMR. When an electron goes through a medium, it slows down. In other words, it loses energy, and it does so by ionizing the particles of the medium. If it is going through a gas, it slows down because it loses energy through ionization of the gas through the gas. Now, the mean energy expended in the gas per ion pairs is denoted by W bar, or the work function. And this mean energy expended per ion pairs in a given gas is constant. In air, that mean energy divided by E, which is the charge on an electron, is approximately equal to 33.97 plus or minus 0.06 joules per coulombs. Joules per coulombs. Alternatively, E divided by W gives us the number of the coulombs of charge released per joules of energy deposited in air. W over E is the mean energy expended in the creation of an ion pairs in air. E over W is the total ion pairs created per joule of energy deposited in air. It's important that you keep this unique distinction in mind. Now, the term exposure, denoted by X, essentially is defined as the quotient of dq divided by dm. dq divided by dm, where dq represents the total charge of the ion pairs generated in air when all electrons, that is both negatrons and positrons, are liberated by photons in a given air of mass dm. But it is also interesting, given the definition of the work function, to note that exposure simply is the ionization charge produced per unit of the energy deposited by the photons in air. And so the SI unit, if you look at this formula, the SI unit of exposure is charge per kilograms. It's charge per kilograms. It's charge per kilograms. In other words, to conclude this definition, exposure is the ionization equivalent of the collision KMR in air for photons. It is the ionization equivalent of the collision KMR in air for photons. Recall that collision KMR is simply defined as the energy transferred to charged particles per unit mass from photons. The energy transferred to charged particles per unit mass to photons. If we define collision KMR as the energy transferred to charged particles per unit mass, then we can relate exposure and KMR. This means that exposure X will be equal to the collision KMR in air multiplied by the charge produced per energy deposited in air. The charge produced per energy deposited in air. The charge produced per energy deposited in air. But keep in mind that collision KMR is equal to the energy fluence multiplied by the average mass absorption coefficient. This would mean that exposure will be equal to the energy fluence multiplied by the average mass absorption coefficient multiplied by the charge produced per energy expended in air. This is air, and this gives us the relationship between exposure and KMR. It gives us the relationship between exposure and KMR. But what do we know? We know that the energy fluence is equal to E multiplied by the particle fluence. So this would imply that exposure can be defined as the energy of a given particle multiplied by the total number of particles per unit cross-sectional area multiplied by the average mass absorption coefficient multiplied by the number of charged particles, the number of ion pairs created per joules of energy deposited in air. This gives us an alternative expression for the exposure in air. For the exposure in air. Now, this formulation will become critical in understanding TG21. Will become critical in understanding TG21. Now, let's look at the relationship then between exposure, absorbers, and KMR. Exposure, absorbers, and KMR. Exposure, absorbers, and KMR. The best way to demonstrate the relationship between exposure and absorbers and KMR is to look at the graph this stepped in centimeters. If we draw the graph of collision KMR, it is a straight line that is decreasing. This right here is collision KMR. But if we draw the graph of absorbers, it has a build-up region and then it decreases. You notice here, the first observation that we can make is that 1. Collision KMR is maximum at the surface. but the depth dose curve has a maximum which is not at the surface. So this is Dmax. So we can divide this graph into two regions. This region is what we call the build-up region. And this region is what we call the equilibrium region. So what we call the equilibrium region. The relationship between absorbed dose and collision camera is defined as, we know that the dose is deposited in a given medium is proportional to the collision camera. So this means that the ratio of dose to collision camera is equal to a constant, and let's call that constant beta. From our previous slides, we had discussed the fact that the dose deposited in a given medium is proportional to the collision camera. Mathematically, that means that the ratio of dose to collision camera is a constant. Let's call that constant beta. In the build-up region, that constant is less than 1. In the equilibrium region, that constant is greater than 1. This region is called the equilibrium point, where charge-particle equilibrium exists. I'm going to draw a line through that region. So this region is what we call the equilibrium region, where transient charge-particle equilibrium exists. And this region is what we call the build-up region. And so in this region, the ratio is greater than 1. In this region, the ratio is less than 1. Here, where charge-particle equilibrium exists, that ratio is equal to 1. Now, what you observe from this graph is the fact that collision camera decreases proportionally with distance. And this can simply be explained by the fact that as the photon beam traverses deep into the medium, it is attenuated, and therefore the flowings decreases with increase in depth. But the dose initially builds up, and then after it has attained charge-particle equilibrium, it begins to gradually decreases proportionately with collision camera. And the behavior of depth dose curve is strikingly different from collision camera, strikingly because of how radiation interacts with a given medium. When the radiation initially hits the medium, what happens is that the electrons are forward peaked, and so the electrons travel a minimum distance, a given distance, which is equivalent to about its range before depositing its dose. That explains why there is a gradual build-up region before the dose reaches a maximum dose. And so from here, we can clearly see that the dose is equal to a constant multiplied by collision camera. But what do you recall? This means that the dose is equal to a constant multiplied by the flowings multiplied by the average mass absorption coefficient. So this formula is the formula to calculate the dose in a given medium. Now, I'm gonna put a double star here, and you should think about it carefully. if you look at this formula, it gives us a simple way to be able to calculate or to be able to develop the relationship between the absorbed dose and the photon energy fluence at a given point. Now keep in mind that this is the absorbed dose in a given medium. This is the energy fluence. This is the mass absorption coefficient. And this is essentially a constant. Essentially a constant. And so if the dose to medium 1 divided by the dose to medium 2 will be equal to beta 1 psi 1 multiplied by the mass absorption coefficient for medium 1 divided by beta 2 psi 2, the average mass absorption coefficient for medium 2, which essentially can be represented as beta 1 2 psi 1 2, the average mass absorption coefficient of 1 2. These are all ratios. Therefore, the dose to medium 1 is equal to beta 1 2 psi 1 2 multiplied by D2. Here's the kicker. If medium 1 is the same as medium 2 and we're looking at the dose at two different points, then this essentially is 1. And so this gives us a very simple relationship to calculate the dose between 2 points, or to relate the dose in one medium to the dose in another medium. Secondly, the ratio psi 1 over psi 2 is defined as the transmission factor. Now, some authors also call it the displacement factor. The displacement factor. What if we then want to determine the absorbed dose in air? To determine the absorbed dose in air, we know that the absorbed dose in air will be equal to beta multiplied by the collision KMR in air. Now, if we assume that charge particle equilibrium exists, then beta will be equal to 1. We're only assuming that charge particle equilibrium exists, in which case beta is equal to 1, and the dose in air will be equal to the collision KMR in air. Let me call this A. B. There is an intrinsic relationship between the collision KMR in air and exposure in air. Exposure, really, if you recall, is equal to the collision KMR. If you recall what we did before, exposure is equal to collision KMR multiplied by the charge liberated per joules of energy deposited in air. So this is equal to the energy fluence in air multiplied by the average mass absorption coefficient in air multiplied by E divided by W air. this is the collision camera in air, which is equal to the dose in air. So what that means is that the dose in air is equal to the exposure multiplied by the energy liberated, the energy deposited per the energy expended per unit charge created in air, this gives us the formula to calculate the dose deposited in air. The dose deposited in air. What about the dose deposited in a particular medium? Now, if we visit this equation, remember this, we're going to come to that now. We know that D is equal to beta multiplied by the collision camera in that particular medium. But if charge particle equilibrium exists, beta will be equal to 1, in which case this will be equal to the energy flowing in that medium multiplied by the average mass absorption coefficient. Remember that this is the energy flowing at the given point in that medium. So the dose deposited in a given medium divided by the dose deposited in air, assuming the existence of charge particle equilibrium, will be equal to the flowings in medium multiplied by the average mass absorption coefficient in medium divided by the particle flowings in air, the average mass absorption coefficient in air. Now, this ratio is what we call the transmission factor. So this will be equal to the transmission factor multiplied by the ratio of the mass absorption coefficient of medium to air. In other words, the dose to medium is equal to the transmission factor multiplied by the average mass absorption coefficient of the ratio of the mass absorption coefficient of medium to air multiplied by the dose in air, multiplied by the dose in air. But we know that let me do this, the dose in air is equal to the exposure in air multiplied by W over E in air. So we can essentially plug this back in here to give us a unique equation that will help us to calculate the dose in medium. This means that the dose in medium will be equal to the transmission coefficient multiplied by the ratio of the mass absorption coefficient of the medium to air multiplied by the exposure in air multiplied by the ion pairs created per energy expended in air. So this gives us literally the dose to any medium. The dose to any medium. And we're drawing closer and closer to the formulation in TG 21. But what you need to keep in mind is that this equation is only true provided charge-particle equilibrium exists. Provided charge-particle equilibrium exists. Now the next thing that we will talk about really is to consider a much more an elaborate theory that can help us to relate the dose in any two medium to each other as long as charge-particle equilibrium exists. Suppose that let's consider a region of otherwise homogeneous medium W, which contains a thin layer or cavity filled with another medium M. So we have, let's say, this is W sandwiched by a thin cavity G. Let's say that we have a particle flowing or incident through that given medium. The dose, this is dW, the dose in the cavity and the dose in the medium. Bragg-Gray cavity theory really provides a means for us to be able to relate the dose in W to the dose in G on one condition, that charge-particle equilibrium exists between these two different partitions. Now, in order, take note about this, in order for charge-particle equilibrium to exist, so that we can apply what we've learned previously, a couple of conditions must be satisfied. A couple of conditions must be satisfied. One, the thickness of the layer G must be small enough in comparison to the range of the charged particles striking it. If the thickness is small enough, then we can effectively assume that the number of charged particles entering G is equal to the number of charged particles leaving G, in which case electronic equilibrium exists in G. 2. The absorbed dose in the cavity is assumed to be deposited entirely by the charged particles crossing the cavity. Let me put it this way. Remember that for Bragg-Gray cavity theory to work, the partition G has to be thin enough, smaller than the range of the charged particles entering it. And if this is true, then we can assume that the number of charged particles entering G is equal to the number of charged particles leaving G. And if statement 1 is true, then we can assume that the dose, the absorbed dose in the cavity, is presumed or assumed to be deposited entirely by the charged particles crossing it. What this means is that if the charged particle equilibrium holds true, then the dose deposited in W divided by the dose deposited in G will be equal to the ratio of the unrestricted mass collision stopping power in W to G. This is equal to the unrestricted mass stopping power in W to G. That's the shorthand way of writing it. Keep in mind that this represents the unrestricted mass collision stopping power average over the spectrum of the primary electrons entering that particular partition. Now recall that the theory requires that charge-particle equilibrium exists, and for charge-particle equilibrium to exist, the two conditions must really be fulfilled. And if that is true, then we can say that the dose deposited in the medium is equal to the ratio of the unrestricted mass collision stopping power multiplied by the dose deposited in the gas. This is a beautiful equation that really provides us a practical way of measuring the dose deposited within a given volume. In other words, the dose deposited in the medium is equal to the dose deposited in the gas multiplied by the ratio of the mass unrestricted mass collision stopping powers. But the dose deposited in the gas is equal to J gas multiplied by W over E, where J gas is equal to specific is a constant known as the specific ionization of the gas. What this means is that J is the ionization charge of one sign produced per unit mass in the cavity, and so the dose to the medium will be equal to J gas multiplied by W over E, which essentially represents the energy, which essentially represents the energy expended per ion pairs created in the medium, multiplied by the ratio of the unrestricted collision stopping power ratios. This is medium to gas. This gives us a summary of the Bragg-Gray cavity theorem. In other words, in accordance to the BG's cavity theorem, the ionization produced in a gas-filled cavity placed in a medium is related to the energy absorbed in the surrounding medium. And this is really a very beautiful theorem. But there is one problem with this particular theorem. The problem is, what if you look at, let's say you have a medium and you have another, this is gas, this is the medium. We're assuming that the walls of this cavity is thin enough and that the volume is small enough such that all the particles that enters this cavity leaves. But what if charges are created, or not really created, what if the incoming electrons from the medium knock off electrons in the walls of this cavity? These electrons are called delta rays. These electrons can either cause ionization within the cavity, which in turn will imply that the measured dose will be greater than the actual dose deposited in the surrounding medium, leading to an overestimation of the measured dose. This implies that if this happens, if delta rays are created, then Bragg-Gray cavity theory underestimates the dose in the given medium. This necessitates a modification of the Bragg-Gray cavity theory leading to what we call the Spencer-Attucks theory. In other words, Spencer and Attucks in 1955 showed that one must consider the effects of secondary electrons in the cavity theorem, and so they formulated what we call the unrestricted stopping power ratios to take into consideration these delta rays. And the fundamental rationale behind the Spencer-Attucks theory is that the dose to medium divided by the dose to gas is essentially the ratio of the restricted stopping power ratios of the medium to gas, taking into consideration the generation of secondary electrons within the walls of the cavity. To write this formulation in details, the ratio of the dose of the medium to dose in gas is equal to the integral of delta E max phi t TE guys, TE. So the remarkable thing that you need to take note about this formulation is that this term Tm accounts for 5 to 10% of the dose due to the track ends. In other words, it accounts for the dose deposited by electron whose energy is below the cutoff energy, the delta. Delta in this formula represents the lowest energy for which secondary electrons can be created in the walls of the cavity. So the whole idea is electrons, this is G, this is W. As electrons traverse the medium, there is a tendency for electrons in the walls of this cavity to be knocked out. And these electrons that are knocked out are called delta rays, and they can contribute to the dose within the gas. But there is a cutoff energy within which this is significant. This lowest energy for which secondary electrons must be considered is simply known as delta. Now, the parameter delta really is not well defined. It's really not well defined and varies from order to order, so it depends what source you are reading. But the whole concept of the Spencer-Attucks theory really is taking into consideration the delta rays generated within the walls of the chamber. Now, before we move on, there are a few terms that I would like to define here. The Bragg-Gray cavity theorem deals with the unrestricted mass collision stopping powers, but the Spencer-Attucks theory relates the doors to the restricted mass collision stopping power with the cut-off energy required to generate delta rays in the walls of the chamber, which essentially implies that the Bragg-Gray cavity theorem really underestimates the dose deposited within the cavity. And so the formulation of TG21 essentially builds on the Spencer-Attucks theory, which in turn relies on the foundation of the Bragg-Gray cavity theorem. Bragg-Gray cavity theorem. So the next step that we will talk about here will be the charge measurement. And we're actually now getting into the meat of TG21. So far, we have talked about the Bragg-Gray cavity theorem and the Spencer-Attucks theorem. So we are going to relate these two fundamental theorems to TG21. Keep in mind that the Bragg-Gray cavity theorem essentially states that the ratio of the doses is the ratio of the average unrestricted mass collision stopping powers if the charged particle fluence is unperturbed. In other words, provided charge particle equilibrium exists. Now, Spencer-Attucks theorem really is just an expansion of the Bragg-Gray cavity theorem, taking into consideration the delta rays. And so the TG25 really begins with the measurements of two important calibration factors. The first that we will talk about is what we call the exposure calibration factor, or the AAPM calibration factor. Now, these particular calibration factors are determined at national standard laboratories such as ADCL or NIS, where the chamber and the electrometer are put in a cobalt 60 beam, and the relationship between exposure and the dose to the chamber gas is determined. Now, keep in mind that NIS knows the exposure, and so it can accurately give us the relationship between the exposure reading, the electrometer reading, as well as the gas measured within the chamber. Now, NX, which is the exposure calibration factor, is simply defined as the exposure per electrometer reading. Now, the electrometer reading here really is the corrected electrometer reading, taking into consideration the ambient temperature and pressure. MC is equal to M raw multiplied by P naught over P T plus 273.2 divided by T naught plus 273.2. In other words, the electrometer reading is corrected for temperature and pressure. Hence, you can clearly see that the exposure within the gas in the chamber is equal to the calibration factor multiplied by the corrected electrometer reading. And this is from NBS, which doesn't exist anymore, or NIS, or ADCL. Keep that in mind, or ADCL. So far, we have seen that the dose to the medium divided by the dose to the gas is essentially equal to the ratio of the restricted stopping powers of the medium to the gas, which implies that the dose to medium is equal to the dose to gas multiplied by the ratio of the restricted stopping power of the medium to the gas. But we have also seen that the dose to the gas is related to the exposure in gas, where the dose in gas is equal to J gas multiplied by W over E gas. So this implies that the dose in medium is equal to J gas multiplied by W over E gas multiplied by the ratio of the restricted stopping powers. Now, clearly, in order to determine the dose in medium, we need to know the exposure in that medium. But the question is, how do we measure the exposure in that particular medium? In order to determine accurately the exposure in a given medium or this particular quantity, J of G, we need to know the exact volume of the sensitive volume within the chamber, and that is almost impossible to determine. But to do this can really actually be determined accurately at NIS. And at NIS, the chamber and the electrometer we have looked at the Bragg-Gray cavity theorem and the Spencer-Attucks theorem, and we have carefully seen that the Spencer-Attucks theorem essentially tells us that the ratio of the doses between two medium, the medium and the gas, is equal to the ratio of the restricted stopping power ratios, mass collision stopping power ratios. And through these, we can actually link the dose in the medium to the dose in gas with their restricted mass collision stopping power ratios. But in order for us to determine accurately the dose deposited within the sensitive volume, we need to be able to measure the exposure within that sensitive volume. In order to measure the exposure within the sensitive volume, we need what we call the air-Kama calibration factor as well as the exposure calibration factor, NX. NX is the exposure calibration factor. Now NX is essentially defined as the exposure measured within the sensitive volume divided by the corrected electrometer reading, corrected for temperature and pressure. So the corrected electrometer reading is equal to M raw multiplied by P naught over P. This is P plus 273.2 divided by P naught plus 273.2. So this implies this means that X is equal to NX multiplied by the corrected meter reading. Remember, this guy is from NIS or ADCL or NBS, the National Bureau of Standards. The National Bureau of Standards. The next calibration factor is what we call the AAPM calibration factor, N sub K, which is simply equal to the AAPM divided by the corrected meter reading. This means that the AAPM is equal to M N sub K. So to connect all of these, recall that the dose to gas is simply defined as exposure multiplied by the number of ion pairs created per joules of energy deposited in gas. This is the exposure in gas. This is just equal to Q gas divided by M gas multiplied by W over E. The charge per unit mass is what we call the specific ionization, J gas, which is just going to be equal to E W over E. Now, if we can use the Spencer-Attucks theorem to develop a more comprehensive relationship between these quantities. So follow with me. We know that D gas is equal to D gas, which is the same as D wall divided by D wall. This is the same as D gas D wall. This is the collision KMR of wall multiplied by beta wall. This implies that D gas is equal to D gas over D wall multiplied by beta wall. You have K, the collision KMR of wall divided by the collision KMR of air multiplied by the collision KMR of air. This will be equal to D gas over D wall multiplied by beta wall K wall C. Let me not use this. This is K wall KC air multiplied by Kx. Remember the exposure for collision KMR of air. This is W over E of air. But this is a constant, 33.97, so it's not really a function of energy. And so we can further simplify this to show that D gas is equal to M multiplied by A wall, beta wall, the ratio of the restricted stopping power of gas to wall, the ratio of the average mass absorption coefficient of wall to gas, Nx, K, E, W over E of air. This gives us the dose to the gas. If you further simplify this equation, you'll end up with this equation. Secondly, recall that D wall is equal to Kc wall. We're assuming that charge particle equilibrium exists, which is equal to the particle fluence wall multiplied by the average mass absorption coefficient of wall. And similarly, D gas is equal to, from what we did before, J gas multiplied by W over E of gas. If we use the Spencer-Attucks theorem, we can combine these two equations to give us X, which is the exposure, will be equal to D wall, the ratio of the average mass absorption coefficient of air to wall multiplied by E of W of air, which essentially will mean that X is equal to J gas multiplied by the ratio of the restricted mass collision stopping power of wall to gas multiplied by a ratio of the mass absorption coefficient of air to wall multiplied by the ratio of gas to air multiplied by a constant K. Now, the constant K itself represents a variety of corrections factors. Now, these correction factors really are needed in order to correct for things like the humidity of the air being measured. Remember that this formula assumes that we are dealing with dry air, but that is not true because almost at all times there is some form of humidity present in air. So we need, and this humidity essentially will affect things like the ion recombination within the sensitive volume. As a result, we have to take into consideration the correction factors to ensure that the exposure that we've measured is the accurate exposure. And so one of the first correction factors that we will talk about is the humidity correction factor, in which case the humidity correction factor, however, removes the effect due to the humidity present in air within the sensitive volume. Remember, the humid air really affects ion recombination, and therefore it is really essential to take into consideration the humidity effect. But what you need to keep in mind is that although humidity is often accounted for, generally the humidity correction factor is assumed to be constant. And this assumption, if you look at the literature present out there, really doesn't lead to any. The maximum error reported is about 0.15 plus or minus 0.15%, which totally is not that terrible. Now, understand that the humidity correction factor considers only the direct effect of humidity in air, but it does leave one question open: what really is the humidity inside the chamber? Let's say you are measuring the depth dose in a water phantom. How can we measure the humidity inside a water phantom? And so it is a very difficult question to answer. As a result, most measurements often assume that the humidity correction factor really is just constant and equal to that of the surrounding air. Now, other correction factors are, you have K-wall, you have K-ant, KST, K-elect, and K-com. So we have to, in general, take into consideration all of these correction factors. K-wall takes into account the lack of charge particle equilibrium in the chamber walls near the cavity. Now, the most important aspect of which is photon attenuation and scatter in the walls of the chamber. Understand that K-wall really affects or is due to two things. Because of lack of charge particle equilibrium in the walls surrounding the cavity, due to photon attenuation and scatter within the wall, it is important to note that this particular concern really is. In addition to the humidity correction factor, we have other correction factors that we have to take into account. And so the term pi Ki, really we have K-wall, you have K-ant, you have KST, you have K-elect, you have K-com. K-wall essentially takes into account the lack of charge particle equilibrium in the chamber walls near the cavity. You need to keep in mind that two important phenomenon occurs within the walls. You have photon attenuation and scatter that happens in the walls of the ion chamber. And because attenuation is always greater than scatter, it means that the K-wall is always greater than or equal to 1. So K-wall accounts for lack of charge particle equilibrium due to photon attenuation and scatter within the walls. This factor, K-wall, is also often written as A-wall, beta wall minus 1 in other AAPM protocols. You should keep that in mind. Kn really accounts for the inverse square law in photon beams. And for spherical or farmer-like cylindrical chambers, so spherical chambers, Kn is approximately equal to 1 or is equal to 1. But for farmer-like or for farmer's chambers that are cylindrical in nature, Kn is actually greater than 1. It often lies between 1.001 and 1.003. Kst is what we call the stem correction factor, and really accounts for the photons scattered into the chamber by the stem of the chamber. It is often less than 1, and KEL is correct for, it's really the electrometer correction factor, and usually it is a correction factor that accounts for an electrode which is made of a material different from the wall of the materials. It is unity if the electrode is made of the same material as the chamber wall, but it will be less than 1 if the electrode is made of a material different from the material of the walls of the chamber. For example, for a graphite farmer's chamber with a solid 1 mm diameter electrode made of aluminum, K-elect is about 0.992. And lastly, KCOM actually corrects for the composition of the walls of the ion chamber and usually accounts for when, especially this KCOM is accounted for when we use a build-up cap that is made up of materials that are different from the materials in which the chamber, the ion chamber is made up of, and it usually accounts for using the build-up cap in which the material is different from the material of the chamber. Let's say you have a chamber here and you insert a sleeve. Now, the material with which the sleeve is made is different from the material in which the chamber walls are made. It introduces errors in our measurements, and to account for these errors, you look at K composition. So there are several factors that really must be considered to ensure that the exposure is measured correctly. You have K-wall, you have K-ant, you have K-stem, you have K-elect, and K-composition. K-composition takes into consideration corrects for build-up caps whose material is different from the walls of the chamber. K-elect really has to do with the fact that we have an electrode that is made with the material different from the materials of the chamber walls, and you have K-stem, which accounts for photons scattered by the stem of the chamber, and you have K-wall. Essentially, K-wall accounts for attenuation and scatter, because if the walls of the chamber are made with a material different from the surrounding medium, then we have to take into consideration the scatter as well as the attenuation that occurs in the walls. The next important calibration factor is the gas cavity calibration factor. The gas cavity calibration factors. Now, keep in mind that the TG21 strives to determine the dose to water by using the charge measured from an ion chamber that relies on the Spencer-Attucks cavity theorem. Now the Spencer-Attucks cavity theorem in turn relates the dose deposited in the surrounding medium to the dose in a gas inside the sensitive volume of an ion chamber. Now, in order for us to do this, we need a multiplication factor called the cavity gas calibration factor. Now, the gas calibration factor, understand that the dose in the gas is essentially equal to the gas calibration factor N gas multiplied by the corrected electrometer reading. In other words, the calibration factor N gas is defined as the dose per electrometer reading, the dose deposited in the gas per electrometer reading. The measurement of N gas is complicated. The formulation is really complicated, and it's really above the scope of this lecture for me to go into the derivation of this gas. But in order to do justice to this equation, you have the dose deposited in the gas is equal to N gas, which is the cavity gas calibration factor, multiplied by the corrected electrometer reading. Now, I am also going to add P ion, which corrects for the incomplete charge collection by the central electrode of the chamber. Now, there are other several correction factors that must be considered in order for this measurement to make sense. But keep in mind that there is an intrinsic relationship that exists between N gas and NX. And N gas is related to NX by, you have A wall, beta wall, A ion, K, I don't expect you to remember that, because I don't remember the equation myself. I'm not even trying to memorize the equation, but the important thing is we should be able to explain how to use this equation. And so I'm going to end this lecture really by summarizing a few things on how TG21 is applied in the clinic. Per TG21, when an ion chamber is inserted inside a medium, in accordance with the Spencer-Attucks cavity theorem, the dose to the medium is equal to the dose to the gas inside the ion chamber multiplied by the restricted mass collision stopping power. We know that this is equal to the corrected meter reading multiplied by N gas multiplied by P ion multiplied by the ratio of the restricted mass stopping power. Remember from our last slide, this right here is the expression for the dose in the gas, taking into consideration the cavity gas calibration factor. Now, P ion is a correction factor that takes into consideration the inefficiency in the total charges, ionized charges collected by the central electrode in the sensitive volume. But for a real ion chamber, the electron flowing is perturbed or disturbed by the presence of the ion chamber. Keep that in mind. For a real ion chamber, the presence of the presence of the chamber disturbs or perturbs the electron flowings, and this introduces some effects that must be taken into consideration. As a result, we will add a couple of correction factors to take that into consideration. So the actual dose measured will be equal to the corrected electrometer reading multiplied by N gas multiplied by the average restricted mass collision stopping power multiplied by P ion, which accounts for the ineffectiveness in the charge collection within the sensitive volume, multiplied by P replacement, as well as P wall. Now we will discuss these factors individually. So this variety of factors must be taken into consideration in order to actually measure the actual dose deposited in the medium. Understand that TG21 provides a means through which we could measure the dose in medium or the absorbed dose to water, either using a water phantom, a polystyrene, or an acrylic phantom. Now, P ion is the charge collection factors. What you need to understand is that inside an ion chamber, some electrons and the cations or positive ions recombine prior to being captured by the central electrode. This implies that because of ion recombination, the total output of the electrometer is underestimated. Now, in order to take into consideration ion recombination within the sensitive volume, we have to include P ion. There are a variety of ways by which P ion can be measured, but the thing that I want to mention here before I move forward is the fact that P ion actually varies with dose rate, it varies with the chamber geometry, it varies with the collecting voltage. Of course, as the voltage changes or as the voltage increases, it decreases the probability of the ion recombination. And really, P ion must be established for each calibration situation. Now, if P ion is greater than 1.05, it is strongly recommended that the collecting voltage be increased to reduce P ion or a different chamber must be used with a smaller p ion. In other words, it is important to keep the value of p ion relatively small, especially in a porous scan beam, where p ion may actually cause a lot of uncertainty in the dose measured. The next calibration factor that I'd like to talk about is P-wall. P-wall. Now, P-wall accounts for the fact that the chamber walls are made of a different material from the medium. And because the chamber walls are made from a different material from the medium, the density is different. And because the density is different, the electron flowings in the medium is not equal to the electron flowings in the wall. But if the wall and the medium are equivalent, then P-wall is effectively equal to 1. Now, in electron beams, thin wall chambers, effectively we can assume that P-wall is equal to 1 for thin wall chambers, since measurements are said to show that ion chamber response really does not depend on wall composition, according to some research. Now, this is only a basic assumption, and often the case is shown to be valid. Now, for photon beams, the situation is a little bit more complicated than for electron beams. But keep in mind that P-wall corrects for the perturbation introduced as a result of the differences between the material of the chamber wall and the material of the medium. Essentially, it violates the charge particle equilibrium due to attenuation and scatter that occurs within the walls. The last that we will talk about will be P replacement. P replacement is a little bit complicated. P replacement has two components. You have P gradient and the P flowings. P gradient and the P flowings. When we insert a cavity in a medium, it causes changes in the electron flowings. That is already well established in our previous slide. Now, the replacement correction factor accounts for these changes in the electron flowings due to the introduction or the perturbation caused by the introduction of an ion chamber. Now, in contrast to P-wall, which accounts for changes due to the differences in the wall material with that of the medium, P replacement has two components. You have the gradient correction factor, P gradient, and you have the flowings correction factor, P flowings. Now, one of the effects of introducing an ion chamber in a medium to measure the dose is the fact that the effective point of measurement really is not at the center of the chamber, where, especially when we're talking about cylindrical chambers, we have a chamber. This is the central electrode, this is the sensitive volume, and this is the surrounding medium. Radiation comes in and deposits dose in the medium surrounding the sensitive volume. Now, using Spencer-Artics or Bragg-Gray cavity theorem, we're able to link Using the restricted or the unrestricted stopping power ratios, the dose deposited in the medium to the dose deposited in the surrounding medium. But what you need to keep in mind is that the dose is deposited upstream from the center of the chamber, which implies that the electron flowings in the cavity is representative of the flowings in the medium at some point closer to the source, because there is less attenuation or build-up in the cavity than in the medium. This is corrected with what we call the gradient correction factor. And really, the magnitude of the gradient correction factor depends on the dose gradient at the point of measurement. In most often than not, per updated TG51, the gradient correction factor is actually taken into consideration by shifting the actual point of measurement or by considering the effective point of measurement. For electrons, where the protocol only where the measurements are taken at Dmax, or where the LINAC is calibrated at Dmax, the gradient correction factor is equal to 1 because there is no gradient. But for photons, the protocol recommends that the gradient correction factor should be based really by taking into consideration the effective point of measurement. Otherwise, you would have to factor that into play in your measurements. And so I find that it is a lot easier to deal with the gradient correction factor by taking into consideration the dose at the effective point of measurement, which is something that we're going to talk about a little bit more details. Now, the next component of the replacement is the flowings correction factor, P flowings. The flowings correction factor corrects for changes in the electron flowing spectrum due to the presence of the cavity. Now, the flowings correction factor really is not as important for photons as they are important for electrons. What you need to keep in mind is that the reason why the flowings correction factor is very important for electrons is because electrons are tiny, and they undergo multiple scattering events within the medium. As they traverse deep into the medium, the velocity decreases or the kinetic energy decreases, which means that the stopping power ratios actually increases. As a result, the electron flowings in the medium changes dramatically, and therefore must be corrected to take into account these fluctuations as the electron traverses in the medium. On the other hand, when you look at a photon actually travels large distances within the medium before they undergo any other interaction. And when they undergo interaction for a larger extent, it leads to a forward peak electron flowings because they are of higher energies. That explains why the flowings correction factor is more important for electrons than for photons. It's more important for electrons than for photons. Now, you can read a lot further about this in Attics, page 255, and you will get this. Now, when we are talking about electron beams, the fluence correction factor has two competing effects. You have what we call in-scatter, and you have what we call obliquity. Now, in-scatter, let's say we have a sensitive volume here, and we're about to measure the charge inside this volume. In-scatter is electrons scatter inwards, and the electrons that scatter inwards contribute to those within the sensitive volume. This is what we call in-scatter. On the other hand, the obliquity effect, electrons just go straight through the sensitive volume and really do not contribute to those. And so what you realize is that the in-scatter effect increases the fluence within the cavity because electrons are not scattered out by the gas, and the obliquity effect decreases the fluence in the cavity because the electrons go through instead of scattering. As a result, really, in order to combat this, pancake chambers or parallel plate chambers are designed with an adequate guarded ring around it, and really it has been shown experimentally that for such chambers P fluence is equal to 1. Now, one of the things that you should keep in mind is that the mean energy for electrons as a function of the electron energy decreases linearly with depth, almost decreases linearly with depth, and it has been shown that the mean energy for electrons in the medium is equal to E naught bracket 1 minus Z over RP. Now Z is the depth and RP is the practical range. Now we're going to talk about this a little bit more in our next lecture. Now here are a few things that you need to take into consideration when dealing with TG21. You may not use this in the clinic, but here are a few summaries that I want to give. The very first is that TG21 essentially gives us a procedure, an accurate way for us to determine the dose to water using an exposure calibrated ion chamber. And because we are using an exposure calibrated ion chamber, the procedure actually begins at a national laboratory such as ADCL, which stands for Accredited Dosimetry Lab, where the calibration factors are determined. You have the N gas, which is the cavity gas calibration factor that essentially converts the dose, the product of N gas and the corrected meter reading gives us the dose measured in the gas, taking into consideration all the correction factors. You have NX, which is the exposure calibration factor. Remember, NX can be converted to N gas through mathematical formulations, but it can also be given to us by the standard labs. And so the very first step really is the determination of the calibration factors. Now, the measurement of the output really can be done in either water, acrylic, or polystyrene phantoms. But when the measurements are done in either acrylic or polystyrene phantom, care must be taken to include scaling factors to convert the dose measured in the acrylic phantom to be equivalent to the dose measured in water. Now, because of the introduction of the ion chamber in, a beam, it perturbs the electron flowings in the beam. As a result, it introduces a lot of correction factors. You have p ion, which corrects for the ion recombination that occurs within the sensitive volume. You have p wall that corrects for the fact that the material with which the wall is made is different from the material of the surrounding medium. As a result, it perturbs or it changes the electron flowings between the medium and the chamber walls, as well as P replacement, which takes into consideration two factors. You have the gradient correction factor and the flowings correction factor, which we talked about. And through the application of the Spencer-Attucks theorem, we are able to connect the dose in the medium to the dose in the gas, taking into consideration the various correction factors. Now, the dose to water is obtained as a product of the dose to phantom medium by two important ratios: the mass energy absorption coefficient between the water and the medium, as well as the restricted mass collision stopping power, as predicted by Spencer-Attucks theorem. Thank you so much for listening. Please, if you have any questions, feel free to ask. Thank you. Bye-bye.